Recording is rolling. It is Monday, February 10th. So I see a bunch of guys have turned in these puzzles here. These are, you guys are from Thursday and Friday. Most of these are fluids puzzles. There's a couple of ideal gas applications here, and there's a couple of thermal expansion, but most of the rest of these are like water fluids question, right? So I'll be scoring those, see how you guys did. You guys remember I gave you guys, of course, page of hints last week. In fact, it wasn't the exact solution, but good page of hints. So see who was able to apply some critical thinking and figure that out. All right, so I'm going to come back to this line. I have for you guys a civil engineering PowerPoint today. This was my undergrad major, well, my major going through undergrad. So I can tell you guys a little bit about what the program is like. And because I did have quite a few students who are maybe interested in something engineering route. So like what all is involved that with the class look like. Right. And then the rest of this week is going to be for toothpick bridges. So tomorrow I'll have you guys in teams. I'll give you guys some toothpicks. Well, not this whole thing, maybe like 100 toothpicks, which is probably approximately that many right there. Right. And then the challenge is we'll test these on Friday. I'll give you guys some gap. I usually do like either 20 or 25 centimeters. Right. So like some gap you have to span. So that's what suppose it was 20 centimeters. Could that be about that long right there? 20 centimeters. Right. So you'll have this gap. I'll set this on top. All right, and then I'll put a gray tray, which will be a little bit of weight, but and then I'll start stacking actual weights. Like bam, bam, bam. We're gonna say who's can hold the most weight. And all you get are 100 toothpicks and glue. So maybe you want to know some engineering principles. I might throw you guys a couple of hints on that front tomorrow. You're gonna have to have some patience, right? Think about designs, put together, right? Right, so you guys good with what we're doing? So you'll get to glue that together Tuesday, Wednesday, Thursday, right? And then Friday they'll be ready to go, and we'll test them on. All right. All right. All right. So actually, back to this line then. Cool Math Cargo Bridge. So a student in another class told me about this program. And I was poking around with all this. Oh, actually, this looks pretty good. Now, I wasn't able to get this actually running on my computer because I think it needs like Flash or something that's not on these dual computers. So probably same thing for you guys, right? But if you get the chance, if you get this on a computer, it does work. You guys see these gaps you're trying to span with bridges? Now, if you just throw some flat planks across, that has no strength at all. So that if you start carrying cargo boxes across just like flat planks, like a rope bridge or something, it's just gonna fall apart, right? But ooh, do you guys see this truss-looking structure? Like they built some triangles here, so that gives it a lot more strength. Okay, a lot more strength, and then you can actually carry some cargo across. All right, so there's a computer game version of building bridges. All right, and what else is involved in building bridges? Ooh, that's the topic for today is civil engineering. So I said that's what I did back in undergrad days. Now this was a 5-year program. Most college programs are like 4 years, so spend an extra year taking these classes. Right? So I was trying to put together, okay, what all classes did I take? And I think this is a pretty complete list of what I take. Maybe we took a couple of extra electives that are on those lists too, but use most of them. Right? Now, when I was going into college, I mean, I definitely had some misconceptions of what it was going to be like. So I had this idea, like, okay, I guess like 4 or 5 years from now, I'm going to graduate and I'll be a full engineer and I'll know all about engineering. I can design and build anything. When I went through these classes, I realized, ooh, that's actually not the case. A lot of these classes, you're just really getting the bare foundations. And a lot of the learning is going to be like on the job of whatever job you end up taking. Okay. You have to take an exam called Fundamentals of Engineering before you're allowed to graduate. And even that, like, if you pass that exam, that won't make you a full engineer yet because to get that, well, you have to practice engineering for a few years. You have to pass a professional engineering exam, which is a whole other thing, right? So this is definitely a process that goes beyond beyond college. Right? What else here? Just the college environment is different than a high school environment, and that's something to be prepared for too. Like high school classes, you guys know, you show up at 8:30 and then you go till like 3:30, right? You're just in school, like class after class after class. And you do that for 5 days a week for 2 semesters in through a class, right? Now, college classes, a lot of these classes are 1 semester instead of 2. And a lot of these only meet 3 days a week instead of 5 days a week. Right. So already you're only in class for like, maybe a third of the time to learn the same amount of content. Like, I know if you go to University of South Florida, uh, they're on a 4-day schedule, so their classes only meet twice a week, right? So a lot of this is on you to learn. Some of these classes I might even recommend taking in college, even if you've already taken it in high school. I did that with uh, this calculus class, Calc 2, and also this class I'm teaching right now, physics. Right? So I took those in high school. I could have tested out and skipped them if I wanted to, but first semester in college, I'll take this again, right? And I'm glad I did because I got a lot more out of them, right? When you see something a second time, then the basic concepts are reiterated again. If they're worded a little bit differently, so okay, right, you learn that much more. You see things from a little bit different perspective, right? Every teacher, every instructor is going to come with their own background knowledge, right? That's kind of an advantage of being in a teaching position is, right? Like I have whatever knowledge I have, right? There are obviously some core things I need to teach you guys, but maybe I know some extra stuff about this, and maybe another physics teacher knows something about a little something different, right? They can kind of hone in on specific things they know, right? And say like again, like you'll be taking physics over an entire year versus you go to college, it's just like a couple days a week for a semester and boom. And they might even throw you some tougher puzzles, but the time you spend in class like learning how to solve things, it's just like really, really fast, right? Right. And you're expected to on your own time figure out everything else, right? Maybe spend more time studying and whatnot in your own time. Uh, just a college schedule looks a lot different than high school schedule too. So there might be a lot of spaces in your schedule. So maybe you have an 8:30 in the morning class and a 9:30 in the morning, right? Usually there's like 15-minute gaps between classes because you might have to cross campus and it might take 15 minutes to walk from class to class, right? And then maybe you have a big old gap in your schedule and you've got nothing until 1 o'clock. And so you got to figure out what do you do with time? Okay, well, probably gonna grab lunch at some point, but I don't want to just like waste my time. So maybe I can go to the library and study, and I'll make that part of my routine. Okay, I know from 10 to 12, I'm gonna go to the library and I'm gonna break over the books and I'm really gonna study this, right? Or I had a part-time job myself in college. I was tutoring math and physics, which by the way, how I actually got really, really good at this job. So like if I hadn't had that tutoring job in college, I either wouldn't be here right now or I wouldn't be as good a teacher, right? Right. So that's where I really learned just that, right? That's a really good way to learn things in general is teach somebody else, right? You get a tutoring job, right? Or just explore your interests in general. Like college is a really good opportunity to do that. There were sometimes like, I got this, few hours window. I'm just going to hop in on other lectures and see what's going on. I can just walk into an astronomy class or to a geography class, just sit in the back. There's hundreds of students. Nobody knows you're sitting there, right? You can just like learn stuff, right? Or whatever hobbies or extracurriculars that you want to pick up on or learn, right? Because you're not going to learn everything in class. A lot of it's going to be up to you and your own initiative. All right, so back to this list here. I remember one of my classes was an engineering overview type class because there's different branches of engineering. Now, civil engineering, which is what I am doing, that's like big static structures. So big buildings, you got roads, let's say like pipes and sewer systems, bridges, right? That's all civil, right? Airports, right? But there's also mechanical engineering. You guys remember those Geneva drives you guys built a few weeks back, right? Ooh, so if you want to do anything like robotics or build like machinery or a giant factory with moving parts, right? Maybe that's more mechanical. There's electrical engineering. If you want to do something that way, that's what computer engineering and industrial engineering, aerospace engineering, right? So all different branches of, right? So if you're on an engineering track, well, what type you want to do? I did have to take a writing class, so right, learn how to communicate, write essays. It's more geared towards engineers. So that's there. This programming class. Does anybody know anything about coding, programming? Some of you guys do? Ooh, that's a really good skill. Really good skill. Now, me, don't ask me anything about that because I don't know much. I really struggled in that class and a bunch of classes. There's another thing too, is a lot of these classes really humbled me. Going through high school, it's like, oh yeah, these classes are a breeze. I'm really good at math and science. And then I hit college and I was like, ugh, I don't know what's going on. So, I guess like a lot of things, like you guys are, sorry, you guys are old enough now to know, say, what your interests are, or start developing this interest, or kind of exploring what you're interested in, and start building skills that are related to those interests. And it's not all going to come from school anymore, right? Like what you had to know in third grade, you could probably just get from your teacher and playing with your friends on the playground. But now you're kind of at the point where you have to say, I really have interest in this or that, and really pursue that on your own time. You have to like, make a time and a space for it on a Saturday or something, right? And a lot of yeah, in high school, I think you can pick up these skills. A lot of you guys are, say programming, coding, sort of thing. So when I took this class, the students who would do something about it because they did it on their own time, they were that much further ahead. And for me, it's like, it's so confusing. I've never seen any of this stuff, so I don't even know what's going on. Right? Well, I had to take an ethics class, right? Learn about different codes, ethics, situations, and stuff. Math. Oh, no, I threw trigonometry on this list. That's usually a class offered in college. I didn't actually take it in college, and probably most students would have tested out of it and not need to take the class. I mean, if you've mastered the topic, right? But you guys know in this class, you see sine and cosine all over the place, right? That's all trigonometry. So if you had to take that or brush up on it, then that'd be available there. If you go an engineering route, you're going to use trigonometry every day of your life or not, so gotta have that skill. But a lot of you guys probably might be actually entering, just going like straight into calculus. You guys know calculus 1 is about rates of change. Calculus 2 is mostly focused on like integration, like adding up small parts into like some aggregate. Calc 3, I remember, was like in 3 dimensions. It's like if you have some hilly terrain, like some 3D terrain, you're trying to figure out what's the slope of that hill on the east side. I mean, it was one application. That was yeah, I remember that 8:30 class. That's where I learned the value of coffee in the morning. Yeah, that made much more sense after starting coffee. Yeah. Ooh, statistics. How many guys are taking stats? Anybody taking stats? Stats? Yeah. Ooh, some of you guys. That's a great opportunity too. When I was in high school, they didn't offer that as a class, but this is one of these classes. I mean, I could probably say that for a lot of these, but especially this one that really changed my view of the world. If you take statistics, you start thinking things in terms of like averages and how much is data dispersed and what's some like probability curve. Yeah, you'll see the world a different way. So it's a good one there. Differential equations. Here's one of these humbling classes. Yeah, I survived that one. So a couple applications from that one. I mean, this is a post-calculus 3 class. I mean, the math gets pretty crazy. I know if you're doing aerospace, you definitely have to have differential. I can tell you why. You guys know in this class, you usually ignore air drag. Like we took the blasters out to the balcony one day, start blasting, and said, okay, let's ignore air drag and basically just treat it as a parabola to see where's the ball going to land. All right, differential equations. I actually saw this puzzle solved with the air drag. Ooh, man, that was a lot of chalk. So yeah, that was fun for someone. Then how many guys ever had an MRI scan done? Magnetic resonance imaging, right? So how this works is, right, they put you in this machine. It's got these powerful magnets that polarizes all the water molecules in you, right? All the H2O, right? And then it changes the field, and there's an electric field change, and then there's another machine that picks up on that. Right. And they can see all details inside your organs. You can see like exactly what does your kidneys look like or something, right? You can see all like 3D imaging inside your body, right? Well, part of the math that's involved in that is something called a Fourier transform. Now, don't ask me what that is. I just know it's involved in MRIs, and it's something that we learned in differential equations. So it's applications of this. Right? All right, science. So nice short list here. Physics 1 and 2. Now, the college version of this and the high school version, they don't 100% overlap, but there's a lot of overlap. What you're learning in this class is mostly physics 1. Now, physics 2 in college is mostly focused on electricity. Now, I know in this class we haven't done anything with electricity yet. I'll do some DC circuits with you guys in a few weeks. So you guys will learn about voltage and current and resistance and that sort of thing, right? Parallel and series, right? So we'll do that. But here they get a lot more detailed and gets a lot deeper. I remember thinking chemistry 1 seemed a lot like high school chemistry, and chemistry 2 was like more advanced and had to do with like rates of reactions. And so I was like, okay, there's that to do there. And there are a bunch of other science classes too that I just didn't have to take for engineering, but much more, right? All right, engineering specific. Ooh, got a whole list here. And most of the slides for the rest of this presentation, I have at least a slide for each one of these. So maybe I'll hit these real fast. So statics is actually this next slide here, right? So hang on to that, right? Dynamics is if you're looking at something in motion, right? There were specific classes just for concrete and steel. Like that was a class, that was a class. because that's most of construction is like those materials. So you have to know like what are all the codes for those materials? How do these materials work? You guys see a little bit of that in this PowerPoint. Thermodynamics, so how does heat transfer? How efficient can a machine be? If you put in a gallon of gasoline, how much useful work can that do? And how much is uh, uh, waste heat? Right? The last week I've been doing with you guys water moving through pipes, right? You guys seen Archimedes principle, Bernoulli conservation flow, Pascal, right? Now that's really basics too. This is actually two classes. There's hydrodynamics and hydraulics. So if you have like water flowing through pipe, it can get a lot more complicated. Like what if we ignore in this class is like the shear force of the water against the wall of the pipe. Um, if you know the size of a channel, say like a storm drain that water's flowing through and like how fast it's flowing through, you can get, is it turbulent or laminar flow? I haven't even talked about that in this class until, right? So yeah, the movement of water can get pretty crazy complicated. Those were two of the hardest classes I took. Soil foundations. So that's a slide I've got near the end of this presentation. Well, what's underneath the school? Like, what's the ground underneath the school? Before the school was built, somebody had to do a land survey and say, what are the layers of what's underneath, right? Now, it's easy to forget what's underneath us because out of sight, out of mind. But, what if you have like different types of terrain, like, clay over there and granite over here, right? You might end up with a leaning tower of Pisa situation where the whole school just like cracks apart and falls apart, right? So you have to know what's going on in the soil foundations, right? Transportation, right? How can you build roads? Right? It's not just a layer of asphalt. There's a whole structure underneath that. How can you make traffic flow? How can you make traffic flow through a city so that maybe on the main boulevard you hit all the green lights or something like that? AutoCAD. So here's a computer program you can design buildings and structures in. Right? Now, one nice thing about being a student taking this class is you can get a student discount so a program that might be hundreds of dollars you can get for much cheaper, say you're a student, or maybe because I had a job on campus. I forget if it was one or both of those. I was taking the class or that I had a job, right? It could be anyway, right? And then here's another misconception I had is I thought, okay, going into this class, okay, by the time this semester's over, I'll be able to design anything in AutoCAD. And it wasn't like that. It's more like they really just teach you the very, very basics of like how to navigate and use the tools. Okay. And if you want to figure out how to actually like master the program, it's really more on your own time. Okay, I got to sit down, I got to make a space and time on a Saturday and design some buildings that I want to build that nobody assigned me, but I'm gonna design it because I want to design it and figure it out from there. Project management. So like, what's the process of constructing the school or anything, right? So some processes have to happen in sequence. Like, okay, well, I can't put in the air conditioning until we've built the structure. And we can't build the structure until after the soil's been tested for foundation, right? So it's like a sequence. But some processes can happen in parallel. Okay, like by the time we have the main structure, okay, we can hire the electrician and the plumber at the same time, and they can each do their own thing, right? Right. So how long does it take to say like build the school? Well, not a single day, right? Because there's this whole process as well, right? Right. What's the most efficient that you could have the process done? Like it's not going to take 10 years to build a school, but it's going to take more than a day. So it's something cringe, right? Right. And so you get this whole flow chart out. It's like, okay, well, here's the sequence. Here's maybe a process we can do it parallel, right? Water and wastewater. So easy to forget about is because a lot of these pipes are just buried underneath the ground. So out of sight, out of mind, easy to forget. But we're lucky to be living in a country where you can drink water straight out of the tap and it's safe to drink. Right? You can't do that everywhere in the world, right? Right. And then what about water that gets flushed down the drain? Where does that go and how's that processed? Right? There's processes to all these things, right? And if they weren't, then we wouldn't be able to live in a society. Yeah.
Terms feel like there's like few rooms where they do
Yeah. College classes like big old auditoriums with hundreds of people in them. Yeah, some of them are. Here, let me see if I go back here, which ones were. And these physics and chemistry classes, those were big auditorium classes. I know there were hundreds of people in there. Not all of these were. Like some of these were small classrooms. I think my calculus classes look a lot more like high school. Statistics, yeah, I think that was an auditorium class. Differential equations, that was auditorium. Now some of these engineering specific, yeah, I think these were closer to high school type. Yeah, a lot of these. Yeah, so really kind of depends. Yeah. Yeah, you could get anywhere from like 30 students to about 300 students. Yeah, somewhere there. So it depends. Yeah, some bigger classes, some smaller classes. All right, so give you guys a quick rundown, whatever I think I can fit in an hour here. Let's look at statics. So, ooh, and later this week, I'm give you some toothpicks. So, to build a bridge, maybe you'd be thinking about the slide. Maybe this could be helpful. Now, you guys know the basic foundation for the foundational knowledge for statics is these boxes right here. I made a poster just for this. So, equilibrium, sum of forces goes to zero, sum of torque goes to zero. That's it. There's your starting point. Okay. Now, here I have a 2D version, and here's a 3D version of that. Okay. But force and torque goes to zero. Right. Now, from that foundation, you can determine what is the tension and or compression in any one of these segments, right? Like this rod right here, this one right here. Do you suppose this one is in tension or compression? And how much? Okay? Because first of all, if it's in tension or compression, it can tell you what materials you could possibly work with, right? Like concrete has a lot of compressive strength, but almost no tensile strength. Like if you try to stretch concrete in a building situation, it'll just pop apart and it's no good for anything, right? But you can compress, and right? Now steel can go both ways. Steel you can compress or stretch, right? But steel's more expensive, right? So now you got this trade-off. So is this compression or tension? And furthermore, how much? Because maybe every one of these segments could have a different amount of stress in it. And if something has just a little bit of stress, then maybe you want like a little thin rod. If it has a lot of stress, well, maybe that would require a big thick rod, right? And you want to match it so that your materials in whatever rods and sizes you're using actually match the necessary conditions, right? Here's what happens if you over-engineer something. Say like, suppose this segment here, or let's say this segment here, suppose it had like very, very little stress in it, maybe a tiny bit. Okay, I want to put a rod there, but only a thin one, right? If you put a big, thick rod there, well, first of all, you're adding more weight to your structure that's not necessary. So now it's putting even more stress on other parts, right? But also you're requiring the cost of your materials is going up, right? So suppose I don't know, some government wants to build a bridge, and okay, we want to build a bridge from here to here, and they the way it works in the States is they contract it out to different companies. So for a bid, there's a bid system. So you might call up like 4 or 5, 6 companies and say, hey, here's what we want to do. Give me a bid, and you're looking for the lowest cost bid is going to win. So one company says, oh, we can do it for $50 million. Another one says, no, we can do it for $45 million, right? And whoever has the lowest bid, they're going to get the contract. This is usually how it works, right? Okay. So if you're putting in big rods where you only need a little tiny rod, well, now that's just unnecessary expense, right? So one way to think of engineering these structures is you want to make it like equally strong or equally weak throughout the entire structure. That you don't want one part to be really strong, one part really weak, because that would not be effective, right? All right. I got maybe it's kind of a fun trivia slide. Is what shape is like the strongest shape to construct with? And the answer ends up being a catenary, right? And how can you create a catenary? Is guys see this chain right here? If you hold either a string or a chain at two ends, it naturally creates a catenary. Now, obviously, you get like a thin or a wide catenary shape, right? But this is a shape that naturally comes out of nature, right? So this is one of these examples of where you can look to nature for inspiration, because the mathematical equation ends up being fairly complicated, right? And if you take this and turn it upside down, you just create the arch version, right? And that could be like the strongest arch you could use, right? And so nature provides a very simple answer, right? But the math is like, it's a lot harder, right? Right. Ooh, I-beams. So you see these used all over the place in construction, and I want to show you guys why. Right, why are these I-beams all over the place? Okay. So I'm going to steal some notes from my last class. Okay. So why build this I-beam shape instead of just having like a big old block beam, right? Make it all steel, right? Well, one is that steel is fairly expensive compared to concrete. So you only want to use as much steel as you need, right? And I see that this one where I've carved out the sides here, it's a lot less material, right? But it's nearly as strong. Like these two might have pretty similar strength, even though this one's more material, more costly, and also heavier too. And that's not necessary, right? So let's go with this shape. Well, let's say I had this I-beam on a couple of supports down here. You guys see a couple of supports, right? And I put a big old weight right in the middle. You guys see on top, got this big old weight right there, a couple of supports down here. See, it wants to bend like a smiley face. You see that? Right. Now, if you look at this from the side, I've got this covered up because I want to see if you guys can figure this out. Right. Look at the bottom part and look at the top part. Which part is in tension and which part's in compression? What is the bottom part in? Tension. What's the top part in? Compression. Well, if the bottom's in tension, the top is in compression. Do you think there's somewhere like there's a gradient in the middle and somewhere it zeroes out and there's maybe zero stress? Maybe, hey, maybe it's that pink dashed line right there. You guys see a pink dashed line? Might be zero stress. Right. Oh, yeah, you guys got these right. Tension at the bottom, compression at the top, or something like that. Right. Well, if it's maximal tension at the bottom, maximum tension at the top, that's where I want most of the material. That's why I got these flanges here. And that's why it looks like an I-beam, right? So you don't need as much material in the middle because there's not nearly as much stress. Right? Like I said. All right, there you go. I-beams. They are useful. So we got fine. Here's another perspective is that this I-beam, you can calculate this, what's called an area moment of inertia. Now you guys have seen rotational inertia in this class. You guys don't do with like mr squared for a point mass, right? But here's the next step of this is to look for like a whole cross-sectional area. So you can calculate it this way, right? And here's an application example of this, right? You guys know this cardboard right here, right? If you take this corrugated cardboard and you tear apart the materials, it's just like, ooh, it got some flimsy, dusty paper that just tears easy. And that's what the whole thing is, just flimsy, dusty paper. Yet somehow you can make a box out of this and throw a bunch of weight in the box and carry it around and the box doesn't break. Why? Because this cardboard is corrugated. So, ooh, hey, that kind of reminds me of a truss system too, doesn't it? That corrugation shape. Right? And from the point of view of all this math, it increases this area moment of inertia, that corrugation shape. It's also why, suppose you have this washing machine here and you reach around the side of the washing machine. I think it has like that indent goes up the side. Right? That's not just there for stylistic reasons. That's also for engineering reasons. Right? It gives it a lot more strength. See, if it was just like flat panel of metal, then it would be really weak. Right? But if you bend it, it gives a little more strength right there. Right? This class, this was fun. This was a class called dynamics. We used to call this physics on steroids. So look at this picture in the bottom right here. I see kind of a pulley looking Atwoody kind of setup here. I see a string connected. Oh, I got this card over here, which maybe has some initial velocity. Okay. Right. Guys, look at this angle beta right here. If the cart's moving, does beta stay the same or does it change? Yeah, it's going to change too, right? Now, suppose you give this card a push, you say, where is it going to be 1.25 seconds from now? I mean, that's a solvable problem, but it's pretty complicated. You guys can see that too. Now, what you can get out of this class is just the very basics of any one of those parts. Okay, I know how to solve Atwoods in this class. I know how to solve pulleys. I know how to work with beta at a basic level, sine and cosine. I know something about kinematic motion. If there's some force in the string, some tension, I know Newton's second law, right? All those little parts lying around you can get out of this class. And then you go to a class like this, which might be a step up to like solving robotics or building something more complicated. And yeah, get the more complex version of that. All right, let's look at, trivia question. You guys see this picture in the bottom left? What is that picture of? The Pantheon. Oh, winner. All right. Got smart students. Be lucky working with the school. Yeah. Pantheon. So that's Roman Pantheon. Was it like 2,000 some years old? Think something like that? Yeah. No, somebody standing on the floor looking straight up. You look at the underside of a dome. That's the underside of a dome. Right? And that's built with Roman concrete. Now, Roman concrete is a little bit different ingredient list than we have today. Actually, I think it was stronger than the concrete used today. And they could build underwater with it, so they could do cool things with it. Now, after the Roman Empire collapsed, a lot of technologies were lost to history for a long time. And nobody actually built anything out of concrete for like almost 2,000 years, right? Until this process was sort of rediscovered, except, well, a little bit different way of making it today, right? So today, here's a simplified ingredient list in this pie chart. Right. So you got different types of aggregate. So coarse aggregate, fine aggregate. So basically large rocks and sand and something else, right? You got water and Portland cement. And Portland cement is the more modern version of concrete. I think it comes out of the 19th century, I think. This Portland concrete. Right? People started building with concrete again. Okay. Now, concrete has a bunch of advantages. One is that it's a fairly cheap material compared to other building materials. It's cheaper than steel, right? Another is it's really strong in terms of compression, has a lot of compressive strength. And A third is that you can pour it in liquid form and it will cure, it will solidify. Now, there's a misconception about that too, which is, I mean, if you don't know any better, you might think, oh, okay, you can pour the liquid concrete and I guess all the water is going to evaporate away and leave the hard concrete. That's not how it works, right? How it actually works is this Portland cement undergoes a chemical reaction with the water. So whatever water was initially in it in the liquid form is still in it. It's still in the cured concrete. It's just a chemical reaction that binds it all together. Oh, and that process can take years sometimes. Remember here in you guys know the Hoover Dam was built back during the Hoover administration, so like what, 1920 something like that. So supposedly it's still curing to this day. So they poured all the materials, but it's just so thick concrete, it's like still setting, still curing. Let's say about this. Remember I said concrete has a huge compressive strength, right? But it has hardly any tensile strength, and that led to one problem that the Romans never could figure out. So what could they do with concrete and what could they not do with concrete? What they could do, they could obviously build domes. You're looking at the underside of the dome right there. They could build walls, they could build aqueducts, they could build like roads or columns with it. They could do all that. What they could not do, we could never figure out, is actually what you're sitting on right now, which is the second floor of a building. Because there's a classroom space underneath us right now, right? Right. So all right, back they tried it out. Said, oh, okay, well, we're just gonna build a concrete floor, but these concrete floors would always crumble because, well, hold on to the idea because that's going to be a later slide. So hang tight in a few minutes. We're going to round back around to that idea, right? But I want to look at these aggregates inside the concrete. You see coarse aggregate and fine aggregate. You know, really, that's a simplification. Ideally, if you want to really strengthen your concrete, you actually want a variation, like a gradation in different aggregate size. It's like large rocks, small pebbles, little sand, little clay. Right. Right. So why? Well, suppose you have just one size aggregate. You guys see this one says poorly graded, right? Or if you look down here in this graph, you guys see the one says uniformly graded. That's the same thing because uniform is like uni, like one. So like one form. Oh, like one size. The one up here is like labeled poorly graded. Okay, and why would that be poor? Right? Well, you guys see these big old gaps between the aggregate. Now that's going to be filled by your Portland cement. But guys, what do you think is the strong part? What do you think is the weak part of the concrete? The aggregate, is that going to be the strong part or the weak part? Strong. And the Portland cement is going to be the weak part. So suppose you have a 50-story building and you're building taller and taller, like the Tower of Babylon or something. It starts to like crack the bottom floor. It's going to crack along these cement lines. Or suppose there's an earthquake because it shakes it all. It's going to crack along the cement lines. So if only we could fill these gaps with more aggregate. Hey, we just need a different size aggregate, right? Couldn't you put like little medium-sized pebbles in there to pack that? But then if you zoom in on that, sort of like a fractal animation, well, okay, now you just run into the same problem at order of magnitude down, right? Now you got gaps between those gaps. And so, all right. Okay, so do you guys see what this is leading to? Is you really want a whole variation in sizes, right? Yeah, you want your coarse aggregate, you want your pebbles, you want your little sand, and so on all the way down. Right? Now, how can you take a soil sample and know what the mix of aggregate is? So that's what this tower of sieves is for. Right? So you take your soil sample, which has all different size aggregate, you pour it in the top, and then every one of these layers has a different size mesh on it, this wire mesh. Right? So near the top, it'll be a large wire mesh that lets through almost all the aggregate except for the large rocks. Right? And then maybe a couple layers down, now it's just collecting the pebbles, and then maybe a couple layers down, it's collecting the sand, and then a couple layers down, collecting like the clay and the silt. It can only make it all the way down to the bottom. Oh yeah, okay, right. And then if you throw in your aggregate sample, shake this for a few minutes, and then pull apart these sieves, you can see how your aggregate separates out. And if it separates out this well graded, do you see this well graded right here? That will maximize the strength of your concrete, or there's a way to maximize the strength, right? Here's what it looks like on a graph. So increasing size going to the right and the aggregate collection going up. If it's well graded, it's pretty evenly distributed. If it's uniformly graded or poorly graded, it's like nothing, and then bam, you get like all one size and then nothing. Or kind of like if this sieve caught everything and then there's no big rocks and no sand, right? It's all like pebbles. It's like, okay, well, that's just uniform, right? And if it's gap graded, well, maybe it's like if you have a bunch of large aggregate here and a bunch of little silt and kind of nothing in the middle. That could be like this gap grade curve. You guys see that? So this well graded will help you maximize strength of concrete. All right. So what is the compressive strength of concrete? Well, here's some numbers. Now, there's different ways to mix concrete. Right? There's here they have ratios of cement to sand to stone. But water is also an important ingredient, right? Water in Portland cement. So that's um, part of the ingredient mix too. Right? Right. And it looks like different mixtures will result in different strengths. I mean, maybe weak concrete could be okay for what we've got here. Fence posts, maybe like sidewalk slabs, kind of like low stake situations, right? But guys, if you're building a 50-story building, do you think those first few floors you want to have some really, really strong concrete? Yeah, maybe we're looking at like this down here. Right. So if you take engineering in an American university, you're going to be working in American units. That's what PSI is, right? Pounds per square inch. So here's the strength of concrete. Somewhere between 2,500 and 4,500 pounds per square inch. Kind of a range there. I think you can go stronger than that too. This is kind of a typical range. Okay. Over on the left side of the table, I did translate the numbers for you guys. So somewhere between 17 megapascal, you guys know mega is a million, right? So that's 10 to the 6. So 17 million pascals to 31 million pascals, right? Pascal being Newton per square meter, right? So that's metric, right? Or here it is in terms of atmospheres, because that's the third way to quantify pressure too, isn't it? Somewhere between like 100 and 300 atmospheres, right? Ooh. Guys, look at that big number right there, 300 atmospheres. You guys know you're sitting on how many atmospheres right now? One. So we're all sitting in one atmosphere of pressure down here at sea level. I bet if you pumped up that pressure to like 300 of what we're sitting in right now, 300 atmospheres, what do you think would happen to the walls of the school? They'd crush. Yeah, and the whole school would just collapse. Right, crush down just by turning up the pressure. Right, do that. Right now, how can you actually test this scientifically? I see a machine here. I see. Hey, guys, look at these cylinders. Actually, I need to bring one of these to school because I kept one of these for a souvenir out of my classes. So I should bring it for a show and tell. But of course, I did the American version of this. So we have 4-inch diameter and 8 inches tall. Right. Now, if I run my calculator, let's do 4 inches diameter, square that times pi over 4. That's a cross-sectional area of, let's call it 12.5 square inches. You guys see that? Right? Then if you put some force on it, what force, however many pounds that is, divided by about 12.5 square inches, you can determine the stress, right? Because force over area, stress is like a pressure, right? That leads to this right here. So what is the relationship between stress and strain? What is stress and what is strain? So stress is force per unit area. So on this machine, I'm smashing, increasing the force on some cross-sectional area. That provides a stress, force per unit area. And that stress results in what's called a strain, which is just a percent change in length. Okay? Now, this picture down here, I have something, it looks like under tension. It looks like I'm pulling something. So that wouldn't really be concrete. Maybe this could be a steel bar down here. Right? If this was concrete, I would definitely have to be compressing it. Okay, let's do a compression example. You guys ready? Ready to have some numbers thrown at you? Suppose you have a concrete bar that's 100 centimeters long. You guys get that? 100 centimeters long. And you start smashing on it. And you smash it until it's only 98 centimeters long. So it was 100. Now it's down to 98. What is the strain? Let's see. Oh, here it is right here. Epsilon strain. Change in length over original length. It was 100 meters long. Now it's 98. So what was the change? 2 centimeters, right? Going from 100 down to 98. That's a change in 2 centimeters. What's 2 out of 100? 2%. 2%. Yeah. So strain is as a percentage, right? So you guys see percent change in length, right? Or see if you guys really follow what I just said. What you suppose, okay, get those numbers I just said, right? Strain equals 0.02, right? Okay. Do you put a unit after that, like newtons or anything like that? No, it's a unitless number, okay? It's a unitless number because it's 2%, 0.02. Right. So what is the relationship between stress and strain? Well, that's what this graph is right here. I say more stress, more strain. Kind of tends up and to the right. Right? The more stress opponent, the more it strains. Right. Now, the first part is this direct relationship. This is called the elastic zone. You guys see this elastic zone right here? Right. Now, anywhere along this elastic zone, if you put some stress on it, okay, it's going to deform a little bit. But then if you take that stress off, it just very simply goes back to its original shape. And it'll just do that. Right? Kind of like if you take a paper clip and just clip 2 papers together and then pull the paper clip off, it just goes back to its original shape. So that's a fun good, okay? And this slope right here is a material property called Young's modulus. See, I can imagine if I had a big old sponge and I smash it, probably doesn't take a whole lot of stress to strain it a lot. Maybe a concrete bar or a steel bar, right, would be a lot stiffer, right? So different materials are going to smash differently, right? So the ratio of rise to run here is called Young's modulus. Hold on to that idea, right? And if this graph was concrete, and I've seen this graph in lots of classes that I took in college too. So it's one of these graphs keeps showing up over and over. Right? If this was concrete, it would rupture right after about this yield strength. You can go right up to the yield strength, and then bam, it just busts apart. You see that? And then the story's done. All right. But if it's steel, suppose it's steel. Oh, now I could stretch it if I want. Now it's steel, right? Well, you get this whole tail on this curve here. You guys see it goes up to this ultimate strength, right? So, right. But see, once you pass the yield strength, you're beyond the elastic zone. Let's go back to the paperclip. So what if you paperclip together like 50 papers, and then next week you take the paperclip off? Now is the paperclip permanently deformed? Yeah, and that's because you stretched it beyond this yield point. Okay. Now it can have even more strength, but it only goes up to ultimate. And then if you keep straining it, keep straining, it actually gets weaker a little bit before it finally ruptures. Guess that? Right. Also, if you keep straining it like back and forth, it'll can actually fatigue and break that way too. That's another aspect. All right. Remember I just said, here, let's go back to the slope. So we're going back to this elastic zone. You guys see this rise over run? Right. Now different materials will strain differently, given some stress. That's this column right here. You guys see Young's modulus? Right. Now I said it's a material property. Here we're looking at steel something. Now this number varies a little bit based on the shape, but hardly anything. Yeah. Okay. Do you guys see the ratio of stress to strain is like, it's 200 something gigapascals. Guys, what is giga? Giga is a factor of a what? Billion. Billion, which is like 10 to the 9, right? Like that. All right. And I have stress units here, either PSI or Newton per square meter, compared to, well, unit less. So rise over run. This would also look sort of like a stress, right? That's what it looked like, right? Okay. And what is the average yield stress? Well, even though Young's modulus is pretty well constant all the way down, because it should be, it's basically has to do with the material, right? Do you guys see that this average yield stress is all over the place? It's like 300 down here and 700 something up here, which is wildly different, right? Because these are different thickness bars. Do you guys see all these different bars? Now they named all these different names like G250 and G550. So it's right? They have different strengths, right? So maybe these different bars can handle it, right? I bet some of these bars are more expensive than other bars. And you say, oh, well, maybe I want the cheap bar, but wait, then it has maybe less strength to it. So, okay, well, maybe I want the stronger one. Now we got a trade-off, right? Got this economic trade-off. Right? Got to solve that. Now this one you guys did do last week. You guys remember thermal expansion? So let's recap this one again. So if there's a change in temperature, got this delta T, right? Then there's going to be a change in length. Most materials, you heat them up, they tend to expand, right? How much, right? Well, how long was it originally? And what's this? Guys, what's this alpha called again? Coefficient of thermal expansion, or here they call it coefficient of linear expansion, right? Because we're just looking at a line. So if it's something that's like a rod shape, then it's mostly just going to get longer, right? It's mostly what you care about. A little thicker, but normally you can kind of ignore that and just focus on one, right? And let's look at this table. Oh, look at that. I got all different materials. They'll expand differently. Ooh, look at these last two rows. This is going to lead to the next slide. Look at these last two rows. Steel and concrete. Hey, you guys had a question on your on that page you guys work on Thursday, Friday. Now, I told you guys to use 12 times 10 to the minus 6. You guys say it's really close to this? 11 times 10 to the minus 6, 10 to the minus 6. Got, 10 times 10 to the minus 6. Right. There's actually a window of values because there's different kind of steel, there's different kind of concrete. So you can make these different ways. Okay. And within that window, those windows overlap. So basically steel and concrete will expand and contract at the same rate, okay? Which is complete luck in the universe. Guys, we're really, really lucky that that's true. Do you guys know why? Do you guys know why? We're really, really, really lucky. Actually, you're lucky right now. It's preventing you from dying right now. That steel and concrete expand at the same rate. Because, That's it. That's it. Yeah. They can expand and contract together, which means you can create this right here. The steel reinforced concrete. For a few minutes ago, I said the Romans never figured out how to build second floors. You're sitting on the second floor right now. Ooh, that's because the steel reinforced concrete, this composite material. Okay. So first of all, how does this work? Do you guys remember here? Maybe flip back to my screen real fast. Right? You guys remember this? We were talking about like I-beams and saying, okay, well, the bottom would be in tension, the top of compression. You guys remember that? Right. All right, let's go take a look right here. Ooh, guys, look at this big old concrete block right here. Look at the, hey, what are these, what are these bars called? Called rebar? Rebar? Yeah. And are these kind of close to the top of the structure? Kind of close to the bottom? Kind of close to the bottom. And you can see why in my animation up here. Because if you're sitting on the floor, isn't it true we all kind of want to buckle the floor and wants to bow kind of like a smiley face, right? And the bottom would be more in tension than top in compression. Now, the compression part, concrete can handle no problem, right? You can compress concrete for, well, up until its yield point, right? But concrete has a tensile strength problem. So if you just had a concrete floor with no rebar in it, it would just crack apart and fall apart in like 2 years. If that, you might be lucky for it to last that long. But you throw in the steel and that steel rebar, now that can handle the tensile strength. Is that right? Now again, to round this back out to thermal expansion, this material only works also because steel and concrete expand and contract at the same rate. If you were here in the school, let's say it's like July 1st, it's the middle of summer. Do you guys think they have the air conditioning running in the school? How about no? All right, so no air conditioning, everything's hot. Do you think everything's trying to expand a little bit? Okay. All right, and then let's say it's like, well, whenever it gets cold in Florida for like one day, right, then everything contracts a little bit, right? So you get these temperature fluctuations, maybe season to season, day to day. And if these materials did not expand and contract together, then everything, would just crack apart and it would all fall apart. Okay. Ooh, speaking of falling apart, okay. Here's one kind of fun solution to this: self-healing concrete. How does this work? And why would this have to work? Because it's like you look at the school or you look at, say, the causeways going across the lagoon or something, and it kind of looks like, oh, well, that could probably last for thousands of years. That could last forever, right? But that's not actually the case. You guys ever seen happened to the old town of Chernobyl? You guys seen that? Because so there was nuclear disaster back in the 80s. People abandoned this town. Right? Actually, I'm just using that as one example, but there are plenty of abandoned towns. And if you look at what happens to these towns after some decades, like nature really starts to overtake them. Guys, if everybody left the school right now and nobody came back to the school until like a million years from now, and you came to this site a million years from now, would you even know that a school was here? Probably not. Like nature overtake it so much that you might not even know that a building was built. Right? Right. So there's a process between now and then, and there concrete is exposed to weathering and rain, and it gets cracks in it and stresses, and maybe you have cars driving over it and people walking it. Right. Right. So, what one way to make this self-healing is I forget the name of the species of some bacteria that you can embed in the concrete, and you can also embed some starch that it can eat. So that when cracks start to form, then now this bacteria becomes exposed to oxygen, and then it wakes up from a dormant state. Maybe it's been dormant for like 25 years, and it wakes up, starts eating the starch. And one of its waste products is, I should add this right too. It's like, well, it'll seal that concrete, right? So self-healing concrete, that's pretty cool. Ooh, let's look at soil foundations. So do you guys think when they built the school, they had maybe check the soil underneath the school? Because if they didn't, is what if one part of the school, you had a bunch of clay over there and a bunch of granite over here. And then every time it rains, which is pretty often in Florida, do you think that clay expands differently than the granite? Yeah, right. And then the rainwater kind of makes its way into the groundwater system, right? So if you're not careful about what's underneath the building that you're building, then, well, you can get this any of these to happen. Here's a leaning tower situation. How is the leaning tower leaning? It wasn't always leaning. It wasn't leaning the first year it was leaning, but the soil underneath it is not even, right? So then you get water and weights on it, and right, it's all uneven, right? Now, of course, we live in a country where there's codes about this, and you have some government official comes out and actually makes sure that, because I mean, who's building these buildings? Well, you have these contractors, and maybe everybody's doing their job. The engineer designs the building to stand and last long enough, and right, the construction crew, and like everybody's doing their part. But if the ground underneath is not even, then the school's just going to crack and fall apart, and now it's a huge waste of resources. And worst scenario, maybe people even get hurt or die, right? Like that. So yeah, so you have to check. what's happening with the soil underneath. This was a whole semester long class, and even after going through that class for a whole semester, I feel like it was just like scratching the foundations of that topic. Ooh, here's a fun trivia. Guys, fun trivia. You guys ever seen these poles like this? Maybe like a gas station sign, something like that, right? So there are rules for how deep you have to dig, and maybe it depends on the soil. Maybe different kind of soil has to be different depths. So that's true. That'd be a factor. But a pretty good rule of thumb. Guys, suppose there was a pole that was 100 feet tall. Right? If you had to guess, pretty good rule of thumb, what's the minimum depth you think you have to dig down for 100 feet tall? Would it be like 2 or 3 feet down? Oh, about 2 or 3 feet down. No, it's got to be deeper than that, right? How deep? About 33 feet. So a good rule of thumb is every 3 feet above corresponds to 1 foot below. Right? Again, that's not the whole rule, but the maybe get you started right there. Right? All right. Ooh, here's a cross-section cutaway of is this AutoCAD? It's either AutoCAD or a similar looking program. Right. Again, when I took this class, I really just learned the bare essentials of like how to navigate the program and how to work the tools, right? And maybe measure some things, right? But if you want to get really good at this, then get hold of this program as soon as you can. Maybe if you're a student in college, you can get the discounted price on this, right? And then you got to make a space and time yourself to just come up with projects that you want to do and just design stuff. And that's really a really good way to learn that, right? Ooh, water treatment, wastewater treatment. Yeah, I think I mentioned we're lucky to live in a country where you can drink the tap water, right? You can't do that in all countries. So I think we get most of our water from the St. Johns River. I think that's right. Of course, it has to go through a filtration process and then comes out of the tap here. Right? And then what about water that you flush down the drain? Like, where's that go? Well, that has to be treated before it can be sent back to the environment too, right? I mean, because these are processes that build modern society. And, if you go back like a couple hundred years ago, before people knew about clean water, how groundwater worked, right? People would like get sick and die, and there'd be these massive outbreaks of all different diseases because people didn't know, right, about germ theory or anything for that matter. So, remember learning that like these water treatment and wastewater treatment is really unique to a lot of individual situations. So, like if you're upstate Illinois or Eastern Florida or like somewhere in Texas, like the water is different in all these places. So it's going to require a unique solution for how to filter it and drain. Right? And here's wastewater treatment. So what do you water like flush down the drain before you send it back into the environment? You clean that out, right? Yeah, like a lot of these pipes are because they're underground, they're out of sight, out of mind, easy to forget it. But if this didn't exist and if this didn't exist, you couldn't really build a society, right? Roads. So see a road, you're just seeing that top asphalt level, but there's a whole story underneath that road, right? You got to build the foundations to build up to it, right? There are details like you have to crown the road so that when it rains, you want the water to run off so that it's not pulling on top of the road. That would be dangerous, right? Things like that, right? I took a traffic class where we also consider things like how do you make traffic flow within a city, right? If maybe there's a private developer wants to build some big development somewhere, right? You're going to know ahead of time, okay, that's going to increase the traffic over here. So now I'm going to have to pick up extra taxes to support the extra traffic flow that we're going to have to build that infrastructure so we can support this new development. I'm going to have to, how can you make a green wave? So suppose there's a giant avenue where most of the traffic is going. Right? How can I time the lights to maximize the flow of traffic? Right? Remember an activity we did? We were out there on an intersection with counters, like counting the cars go by. Something. All right. So, I got that fit in just in time. So it's a quick rundown of civil engineering and that path in college. If you go that path right there. Right. So tomorrow I'll give you guys some toothpicks, and you guys gonna be building some bridges.